Hello students, here we are going to discuss about second unit of computer vision called shapes and regions. These are all the topics we are going to discuss. Let's we see one by one. Notes are available in the description part. You can download it. Shape and region analysis is all about understanding how objects are structured, their geometry, and how they are arranged in an image. These techniques are really useful for tasks like recognizing objects, classifying them, or even tracking them in different applications like medical imaging, industrial inspection, robotics, or surveillance. In this unit, we will focus on binary shape analysis, boundary shape analysis, and region shape analysis. Before discussing the topic in detail, let us conclude the hierarchy of these contents. I categorized different topics under these five important broad areas. Let's see first binary shape analysis. It means studying shapes in images that have only two pixel values, 0 for background and 1 for foreground. Here, the word shape refers group of connected foreground pictures that form an object. In simple words, we are looking at black and white images and trying to find meaningful shapes from them. The main purpose of binary shape analysis is to identify, label, and measure the shapes in binary images. We do this so that these shapes can later be used for recognition, classification, or further geometric analysis. In short, this step prepares shape data for the next level of processing. To do binary shape analysis, we follow some important steps. First, we check the connectedness of pixels. Then we label and count the objects. After that, we apply size filtering to remove unwanted small shapes. We can also take different measurement of shape and sometimes simplify or represent the shape in another form. These steps make analysis process organized and effective. Binary shape analysis has many useful applications. For example, it can be used to count cells in microscopic images. It can detect defects in manufacturing part. It also used in traffic surveillance to count and classify vehicles. Handwritten character recognition also depends on this technique. And finally, it is important in medical imaging, especially for detecting and extracting tumor boundaries. Now we see about connectedness. It's the first topic under binary shape analysis. It means how pixels are grouped as neighbors to form objects in an image. Two pixels are connected if they are next to each other and have same value. We mainly use three types: 4 connected, 8 connected, and mixed connectedness. 4 connectivity means a current pixel can be connected with either top, right, below, or left hand side pixel. That can be represented like this. Let's see one numerical example. Take the first one. Now this is the current pixel. If it is a current pixel means you have to check any other pixel having the value 1 either in left side, top, right side and below. Here left side the value is 0 and top there is no information, right side the value also 0 and below the pixel value is 1. So there is a connection between this one and this one. Now this pixel having the current pixel. You can repeat this operation. So left hand side there is a 1 is there. So this one is also connected. This process is not completed. You check the top of the value. It is already visited. Then you can move the right hand side and bottom. So there is no 1 is there. So you can move to this pixel. Now this pixel is a current value. You can check the left pixel. It is 1. Right pixel already visited and below pixel. So these values are connected by means of 4 connectivity. You can redraw this binary image that can be looks like this. Then you can give the unique color for this particular object so that you can tell how many objects present in this image. Here there is only one colored object is there. So the number of object is 1. Suppose if the binary image having the value 0 instead of 1, now you apply the same process. This one having no connectivity from any other ones in this image. Left hand side, top, right and below. So this is the separate object. Then do this operation in another ones. So for this one, these three ones are connected. Now the image can be drawn like this. It can be denoted in different colors so that you can identify two objects present in that image. So in this way, the number of objects can be found. Let's see one real-time example. Suppose this is the original image. First we have to convert this image into grayscale image, then convert into binary image. From this binary image, the pixels values having zeros and ones only. Apply the 4 connectivity, you can find how many connected objects are there from this image. The result may be like this. From this output we can tell 6 or 7 objects are there including these small parts. But actually only one image is there. By applying 4 connectivity, we can get less accuracy for real-time images so that we can move to the 8 connectivity method. In 8 connectivity, along with 4 directions, we also include the diagonals. That can be denoted here. In this diagram, D is not diagonal, D is the direct value, that is top, bottom, right and left. X means diagonal information. This 8 connectivity is illustrated in this image. It is the combination of 4 connectivity along with the diagonals. Let's see this example. If you are applying the 4 connectivity method, we can identify this is the object 1 and this is the another object and this one is the third object. But in case of 8 connectivity, the same object, there is a connection between these two ones by means of diagonal. So it is treated as a single object. So in this case, we can identify only two objects. So when you are applying 8 connectivity instead of 4 connectivity, this image can be identified as single object. And this one, the excellent example for identifying the difference between 4 and 8 connectivity. Let's see the image. This is the equivalent binary value. If you are applying the 4 connectivity here, there is no connection between this one. So this one is the separate object. You can apply 4 connectivity of all the ones. Every ones are single object. If you are giving the different colors, you can easily visualize it. So there are 9 ones are there. So 9 components are identified by the 4 connectivity method. But in case of 8 connectivity, these two ones are connected. In this way, all the ones are connected. So the output tells there is only one object present in that image. Let's move the next topic. Object labeling and counting is used in binary images to identify and analyze shapes. First, each distinct connected object is labeled with a unique number, so it can be separated from others. Then the objects are counted, which gives us total number of unique objects in the image. So this process helps in both recognizing and quantifying objects in an image. Let's see how object labeling and counting works. We start with binary image where the foreground pixels with value 1 represents objects and we start with a binary image where the foreground pixels with value 1 represents objects and the background pixels with value 0 represent empty space. Next, we do connected component analysis using either 4 connectivity or 8 connectivity to decide which pixels belong to the same object. After that, we assign labels, giving each object unique ID like object 1, object 2 and so on. Finally, by simply counting the number of labels, we get the total number of objects present in the image. See this example. Apply the 4 connectivity. It can be identified two objects like this. It can be labeled in this way and giving the unique color and conclude the result like this. Finally, you tell the total number of objects present in the image is 2. The next topic is size filtering. Size filtering is a binary image processing technique used to remove objects that are either too small or too large based on a predefined size threshold. The purpose is simple. First, it helps eliminate noise like tiny unwanted objects or irrelevant large regions. Second, it keeps only the objects that fall within the expected size range for proper analysis. Now let's see how size filtering works. First, All connected components in the binary image are labeled. Next, we do size measurement, usually by counting the number of pixels in each object. Then remove objects that are either too small or too large based on predefined threshold. Finally, we get the output, which is cleaned binary image containing only the object of interest. In this example, the number of pixels is too large, up to 400 pixels. The objects are already identified and the number of pixels for each object is listed here. Now we can do the size filtering operation based on this given threshold value. This value tells the object pixel count lies between 50 into 250. First object having 150 pixels. It is comes under in this range. So we can keep this object. Second object having only 5 pixels. So we can remove it. Third object contains more than 250 pixels. So third object also removed. So only you can keep object A only. So that can be illustrated here. Let's see one complete numerical example. So in this example, the image is given like this. First you identify number of objects present in the image applying either 4 connectivity or 8 connectivity. In this example, I apply 8 connectivity. I found 4 different objects are identified. I give the labels like this and give the list number of pixels of each object by means of one threshold value. Here the threshold tells the pixels counts are more than or equal to 3. Except object 3, these 3 objects are eligible for this condition. So you can simply remove this object and redraw the remaining object as a output. In this way, the size filter operations can be achieved. Let's see one real-time example. If you are applying either 8 connectivity or 4 connectivity, after that identify the number of objects present in the image and list the number of pixel count for each and every object. Give some threshold value so that you can remove the tiny object. These are all the unwanted objects. So the output is noise-free and cleaned binary image. Next topic is distance functions. Distance functions measure how far each object pixel in a binary image is from the nearest background pixel. They help us to understand the shapes, structures, simplify shapes, and support tasks like skeletonization, shape matching, and feature extraction. Suppose this is the given image. First you identify the boundary pixels, how far it located from the border. This distance is 1 unit. So all these boundary pixels having the value 1 here. In the next iteration, you can identify this object pixel. This is the distance transform. The highest value present in the distance transform is 2. This is called local maxima. Let's see another example. In this example, we identify first the outer boundary. It is represented as 1. Then identify the inner boundary. It is represented as 2. That means the distance between the border and this location having the 2 units. Do this process until you reach the center and this value is 3. This is the distance transform and 3 is the local maxima. And we should know what is the use of distance functions. From these two examples, we can identify this local maxima. From this, we can achieve the data compression so that we can reduce the storage space. After storing this local maxima value only, we can regenerate this entire picture information. Let's see how to achieve compression and decompression using distance functions. First, we convert the binary object into distance transform. Next, we identify the local maxima from the distance transform. Then we store only these maxima which represents a compressed form of data. Finally, during decompression, we reconstruct the full object by spreading the values downward from these local maxima. Let's see this example. First, we identify the border and local maxima. Store only the local maxima. This is called compression. So instead of storing all the pixels, we are going to store only one pixel information. During decompression, first we write the local maxima value at the center, then draw the outer border. Repeat this process until you reach the complete shape. Then finally write the full picture information. So in this way, compression and decompression can be achieved by distance functions. Next topic is Skeletons and thinning. A skeleton is a thin version of a shape, usually just 1 pixel wide with capture its overall structure. Think of it like shrinking the object evenly from all sides toward the center until only the center lines are left. Those lines form the skeleton. The key idea is that it preserves the topology and the overall structure of the original shape even though it is much thinner. From this image, this thick rectangle can be represented as a thin line. In the same way, this ring shape can be represented as a thin circle. Let's see in one numerical example. Suppose this is your object means the skeleton of this object is like this. Next is thinning. Thinning is a morphological operation that gradually removes boundary pixels of an object until only a skeleton line remains. It's one of the main methods to create skeletons. The key point is it makes the shape thin while preserving its connectivity as shown in the example. When performing thinning, a pixel is removed only under certain conditions. First, it must be a border pixel, meaning it touches the background. Second, removing it and does not break the connectivity of the object. That means the shape should be stay connected. And third, it must not belong to the skeleton line because those central pixels must be preserved. A border pixel is defined as a pixel whose value is 1. So it's part of the object and at least one of the 8 neighboring pixels is 0. That means it touches the background. And see this example and identify these pixels are boundary pixels. So these pixels are removed, only the remaining pixels are redrawn. So you achieve the thinning process. Thinning process gives the skeleton of the particular object. Let's see some real-time applications of skeletons and thinning. The A can be written in any form, but by means of this skeleton, we can identify the character is A. Up to this, we discussed about binary shape analysis. Now we can move to the boundary-based shape analysis. This can be treated in two ways. The boundary of static images can be identified. Sometimes the object size can be changed dynamically. In such situation, active contours is the method to identify the boundary information. In computer vision, understanding the shape of an object is very important. There are two main ways to represent the object. One is region-based analysis, another one is boundary-based analysis. Region-based analysis using all the pixels inside the object, whereas the boundary-based analysis using only the pixels along the edges or outline of the object. These methods helps us to analyze and process shapes more effectively. So from these two analyses, first we are going to see about boundary-based shape analysis. Boundary tracking extract the outline of objects. It starts from the boundary pixel and follow connected edge pixels until the contour is complete. This gives an ordered set of boundary points, which we use for recognition or further processing. Boundary tracking is important because it reduces computation. Instead of processing all pixels, we only focus on boundaries. It is also helps in shape analysis since the outline gives the key information about objects. Boundaries can be used for compression, storing only essential points. They are also useful for recognition tasks. And finally, they serve as the foundation for many other computer vision algorithms. How this boundary tracking works means it takes the binary image, it selects the starting pixel, particularly top left corner, and traverse from one direction. Check the neighbors to find the appropriate boundary pixels. Repeat this operation up to it reach the starting pixel. These are all the different methods available to track the boundary informations. Here chain code is in our syllabus, so I choose Freeman chain code tracking method. Suppose this is the given image, we have to find the boundary pixels values. For this, Freeman use this kind of code. These numbers tells the direction of the boundary pixel from the current pixel. It can be represented here. Take the first pixel, that is top left corner. Now these are all the surrounding pixels for this current pixel. I can write it here. Start from any one location. I can start here. That means from the west direction. Then traverse in the clockwise direction and reach the next one pixel. This pixel present in the east direction. The corresponding code is 0. So I add 0 here. Now I can move to this, identify the next pixel. Next pixel is there. Then this is the surrounding pixel value. I can represent it here. And this is the last pixel you visited. Start from this position and do the clockwise direction traversal. And you can reach again the east direction. That means again you can get the 0 value. Now you are located here. This is the current pixel and these are all the surrounding pixel. I can represent it here. From this current pixel, this is the previous point. So you can start traverse like this and you can reach this place. This is south direction having the value 6. So write 6 here. Now this is the current pixel. This is the last pixel you visited. So you can start traverse from this direction. You can reach this south direction again. So the next value is also 6. So repeat this process until you reach the starting point. Now this is the final Freeman code. It can be illustrated like this. So in this way you can identify the boundary points and generate the code like this. Boundary tracking is useful because instead of storing all the pixels of an object, we only store the sequence of boundary pixels. This makes the representation more compact and meaningful. Why chain code means it gives us compact and analyzable way to represent boundaries, making it very useful for shape analysis, recognition, compression, and other computer vision applications. Now let's see what is boundary descriptors. Boundary descriptors are important in computer vision because they help measure the size and complexity of an object's shapes. The types of boundary descriptors are boundary length, Fourier descriptors, and chain code. Chain code we already seen in this example. So we will see these two types only. Boundary length measure is nothing but the total outline of the object. That means perimeter of the object. So perimeter is one of the parameter to describe the shape. The calculating the perimeter is very simple. You just count the boundary pixels. Let's see this one example how to count the boundary pixels. Suppose this is the given image. You can start from here and do the traverse from the clockwise direction. So the coordinate point is 1, 1. So you can go to this 1, 2 and 1, 3. So there are 3 pixels are there. So you can write 3 units in the top boundary pixel. From the right side, you can also start from this pixel and count the number of pixels. Here also you can have 3 pixels. So in this way you can travel along all the sides. You can note the number of pixels. Finally you can add it. You can get the value 12. So 12 is the actual perimeter value getting in this way. Don't count the number of phones in a normal way. You can count the each and every pixel again and again for each side. So you can get the value 12. This is in the case of 4 connectivity. Suppose if you are applying the 8 connectivity, so you can start from here, traverse from left to right. So the count is 3. Here also count is 3. You can repeat the step for all the sides. You can also get the same value for 8 connectivity also. For 4 connectivity and 8 connectivity, you can get the same value because this image is symmetric image. That means it is a squared image. Suppose if you are taking some other image, now you can calculate the 4 connectivity and 8 connectivity value. So 4 connectivity means you try to reach right hand side, left hand side, top or bottom. So in these 4 direction only. So if you are starting from this point, you try to reach this point means first you go this location and this point. So you need 2 steps. That means 2 units are needed. So it can be noted here. Suppose this is your current pixel means you can move first in this direction, then reach this pixel. So you again need another 2 units. So totally 4 units is the boundary count when you are using the 4 connectivity. In case of 8 connectivity, this is the starting point means you directly reach this position. So the distance is root 2. In the same way, you can start this point and reach this one diagonally. So again you can get the root 2 value. Finally, you can add this value. Finally, you can get the 2.82 units. Why this diagonal distance is calculated as root 2 means if you are directly reach this position by skipping these two values. This is looks like the right angle triangle. So this distance is 1 unit, this distance is another 1 unit. By Pythagoras theorem, this value becomes root 2. Boundary descriptors are important in computer vision because they help measure the size and complexity of an object's shape. Instead of just looking at the area, we can compare objects by their boundary lengths. For example, a circle and square with the same area will still have different boundaries. This makes boundary descriptors very useful in tasks like shape recognition and compactness analysis. So for this boundary based shape analysis, the next topic is Fourier descriptors. Fourier descriptors are a mathematical way to represent an object's boundary. They are obtained by applying the Fourier transform to the boundary coordinates. This method provides a compact and robust description of shape. It's suitable for static objects, but by applying proper normalization, Fourier descriptors can also achieve invariance to translation, scaling, and rotation. In simple terms, we treat the boundary as a signal and analyze it using Fourier transform. The steps are: first find the boundary pixels, then identify the corresponding coordinate for that pixels, then convert that coordinate into complex numbers. These are all treated as the sequence. These complex number sequence are treated as a signal, then apply the discrete Fourier transform. Let's see this in one simple example. From this image, these are all the boundary pixels. It can be identified here. Then write the corresponding coordinate values for these boundary pixels. Then write it as a complex number. Treat the x coordinate as the real part and the y coordinate is the imaginary part. Why the complex numbers means the signal should be in a compact manner. Here, the two difference values are integrated in a single unit. So this complex number sequence can be written like this. Here we have totally 8 signals are there that can be represented as small z of 0 up to z of 7. Now you can apply the discrete Fourier transform. This is Fourier transform formula. It starts the value from 0 to 7, that is finite number of count. So this is called discrete Fourier transform. And note this is small case z, this is the capital Z. This capital Z means this is the value you need to find which is present in the frequency domain. But this small case Z is the signal we already have. So first you apply the value u equal to 0. If you are applying small u as 0 means this entire value becomes 0. So e power of 0 is 1. So you can get capital Z of 0 is equal to summation of k equal to 0 to 7 small z of k. That means if you are applying the k value 0 to 7, you can get the expression like this. That means you simply add these 8 signals. So I rewritten the expression here. Then I try to add the real part and imaginary part separately. Both the values are 16 only. So capital Z of 0 equal to 16 plus 16j. We know the total signal count is 8. You can divide it. Finally, you can get 2 plus 2j. That means 2 comma 2 is the center point of the given image. So when you are applying small u equal to 0, you can get the center point of the image. In the same way, you can apply 1, 2, 3 up to 7 values. Then you can get the different types of information from the image. Suppose if you are applying u equal to 1, then this value like this. After applying all the values, you can get the result like this. If you are adding this value, it becomes 0. This calculation is too complex, so you just try to understand what is the meaning for when you are applying u equal to 1. It becomes 0. So I listed for all the calculations. So this is the entire signal result. From this result, these three values only non-zero values. So you can take these three descriptors only to reconstruct the image. that can be illustrated in this diagram. So you know the center point and you know the Z3 value and Z5 value. From this we can reconstruct the entire square image. So here we can convert a shape's boundary into frequency components. Low frequency show the overall coarse shape. High frequency captures fine detail like corners or noise. We don't need all frequencies. Keeping just a few descriptors give a smooth noise-free shape. So up to this we are discussing boundary tracking can be happened in the static images. Suppose the image size can be changed dynamically means you can apply the active contours method. In this analysis, we have to study the shapes that can bend, stretch, or change slightly, but still it recognizes as the same object. The reason for using deformable shape analysis is in real world, objects rarely look exactly the same in every time. For example, in handwriting, everyone writes a letter like A differently. In human body, people move, bend and change poses. In medical images, organs may shift or deform, but they are still the same organ. Deformable shape analysis helps us to recognize these variations as the same class of object. One of the most popular deformable shape analysis is the active contour model, also called SNAKE. An active contour is a flexible curve that moves across an image to detect and locate object boundaries. It works by set of control points. These points form a curve, and curve automatically snaps on the object edge in the image. The behavior of the curve is controlled by two types of forces. One is internal force, another one is external force. By balancing these two forces, active contours adapt themselves to the true shape of the object, making them very effective in shape analysis and object detection. Active contours work in four main steps. First, we place an initial curve near the object. Next, two forces act on the snake. First one is internal energy, which keeps it smooth like a rubber band. And second one is external energy, which pulls out towards the strong edges and corners. Then the curves move step by step and close to the edge. Finally, when the forces balance, the snake locks on the object's boundary. So, active contours automatically adjust to outline objects in an image. It takes multiple iterations to complete this task. So it initially start from this area and finally cover the exact boundary of the irregular shape of any object. So in this way, active contours are works. Let's see one simple example. Suppose this is the given object. We know the boundary of the object. First draw the rough outer line called snake. Then two types of forces can be applied, one from the snake, another from this object. That can be illustrated here. Then this snake is moved toward the boundary of the object. After multiple iteration, it reached the exact boundary of the object. Finally, the snake is perfectly fit on the boundary of the object. So this is the working principle of active contour. So the next part of shapes and region analysis is region-based shape analysis. Like boundary descriptors, here region descriptors are there. Region descriptors are nothing but some numerical representation that tells the attributes of the image like size, location, and overall form. In a boundary descriptor, it tells the boundary related values. In region descriptors, it tells the inner values, that means more information about the object. So the region descriptors can be identified by finding the area, centroid profiles and moments. The first region descriptor is area. Take this example, just count the number of pixels, that is 9. So this is the area. You can compare the two images by means of these values. So area of this image is 9, area of this image is 6. If you want to compare the two images are same or not means, you can use these two numbers to identify the result. The second parameter is centroid profiles. In the same example, so this is the center point. So this is called centroid. The coordinate value is 2, 2. and the centroid profile is nothing but we have to find the distance between this center point from the boundary value. I can draw the image again and find the distance between the boundary values and the center point. First you identify the top pixel. So distance is 1 unit. In the same way, you can identify the remaining 4 directions. In this example, all the directions having the same value, that is 1 pixel distance, and also find the diagonal distance. We already know if you are reaching this point diagonally means the distance is root 2. Then write the center point. These are collectively called centroid profiles. So centroid profiles are nothing but center point along with the distance between the center point to the border pixels including the diagonals. Let's we compare two images using centroid profiles. For this image, the centroid profiles are listed here. This is the second example. The center point is located 3, 3 and the distance between the boundary and the center is 3 for all the top, right, left and bottom directions and diagonals having the distance root 2. So this is the centroid profiles. Using these numbers, we can compare and tell the equivalence of these two images. And the last one is moments. Moments are mathematical way of describing the shape and distribution of pixel intensities in an image. Simply, moment is a weighted average of pixel values. They are very useful because once an object is segmented, we can use moments to calculate important properties like its area, centroid, or orientation. So, moments acts as a fundamental descriptor to analyze and understand objects in an image. For this example, we can easily identify the center point, that is 2, 2, because this image is a symmetric image, that is square in shape. But in real time, most of the images are irregular in shape. We cannot easily identify the center point of this image. So we need a proper mechanism to identify the center of the image even the object is irregular. So moments give the solution for this. This concept is coming from the physics where it represents mass distribution. In images, we treat each pixel's intensity as mass and its position as the location. Here, P and Q are the moment orders. By changing the values, we can get the different informations. Here I show the two images. First one is the binary image. It contains the value 0 and 1. We already know 1 is the actual object. So this is the intensity value. X, Y is the coordinate value. Suppose you can take this position. You can assume this is the first row and this is the first column. This is the second row. This is the second column. So the coordinate value is 1, 1. So XY value is 1, 1 and the intensity of XY value is 0. In the same way, in grayscale image, this is the 1, 1 value and the intensity value is 10. The main point is binary images always having the intensities value either 0 or 1. In the moment calculation, we are always taking the intensity value 1. If you are choosing the intensity value 0, this entire value becomes 0. Note this point, this can be useful for upcoming problems. There are two types of moments are there. One is raw moment, another one is central moment. First we see what is raw moment. This is the formula for raw moment. By applying the different values for P and Q, you can get the different information from the object. Suppose if you are applying P and Q as 0, that means M00, you can get the area of the object. If you are applying 10, it gives the x coordinate value of the center point. If you are applying 01, it gives the y coordinate value of the center point. So these two values combinedly give the centroid of the object. If you are applying P and Q values are 20, 02 and 11, you can get the orientation and elongation and covariance information of the object. Why you are giving the values like this means first one is the 0th order, second one is the first order and third one is the second order. Don't confuse this term why 1 is represented as second order. The order means if you are adding these two digits, it becomes 0 means it is 0th order. Here, if you are adding these two values, you can get the value 1. So this is first order. If you are adding these two values, you can get the value 2 means this is second order. In this way, third order, fourth order, that means higher order moments also calculated. It gives more complex information about the image. We can see first two orders for upcoming example. First you take the zeroth order, that is area of object. This is the simple image having the value zeros and ones. So these are all the actual object. So we don't bother about the zero intensities. So take the coordinate value for these ones here. Assume that this is the first row, second row and third row. First column, second column and third column. So the corresponding coordinate values are there. Now write the intensity value for each coordinate values. So all intensity values are 1 only. So if P and Q are 0, these two values becomes 1. So ignore these two terms. So you just add the intensity values available for this calculation. So all values are 1s means finally you can get the value 4. So M00 is equal to 4 means it is the area of this object. Let's move to the first order moments. First I apply 1 0 and then 0 1. If you are applying 1 0 to PQ, P value is 1 means X, Q value 0 means this value becomes 1. So ignore this value. So the equation is looks like this. In the same way, if you are applying 0 1 means this value becomes 1. You can multiply Y into intensity value. So the equation is like this. After computing these two values, you can divide the area value, then you can get the corresponding x and y coordinate value of the center point. Now I am going to apply this value. X is nothing but all the x coordinate value multiplied with the intensity value. All the intensity values are 1 only and these two values are the x coordinate value for this pixel. Now you can get the value 8. In the same way, you can apply the value here. Here, the y coordinate values are multiplied with the intensity value. So the y coordinate values are 2, 1, 2, 2. So these values are multiplied with the intensity's value and get the result. So this value becomes 7. So M10 is 8, M01 is 7. After dividing by the area, you can get the value 2 and 1.75. So the center point is 2, 1.75. So applying different combination of these values, you can get the different information from the object. So let's move the second type of moment called central moments. This is the formula for the central moment. Here xc and yc is the coordinate value for the center point. Why it is called the central moments means it is highly related to the center point. So even though this object is changed in different position, this calculation is based on from the center point means the value cannot be changed. But in case of raw moment, the calculation is totally based on the coordinate values for the pixel. So if the object can be changed in position means the results also changed. So this central moments is totally invariant for the different translations. From the previous image, we already found the area of the image and the center point. I can take the same image again and identify the mu20 and mu02 and mu11. That means second order of central moments. If you are applying P as 2, Q as 0 means this value becomes 1. So the expression looks like this. And intensity value always 1. So you can write this value corresponding x value minus center point of x value whole square. So in this coordinate, the corresponding x value is 1, center value is 2. So 1 minus 2 whole square equal to 1. So in this way, you can get all these values. Finally, you can add this value and get the result as 2. In this case, P value is 0, Q value is 2. So this value becomes 1. So your expression is y minus yc whole square into intensity value. That can be calculated and listed here. Finally, you can add this value, you can get this result 0.75. In the same way, you can apply 1, 1 in P and Q values. You can get this value like this. So 2, 0.75, 0 are the result from the second order central moments. Here, mu20 represent the variance along the x-axis. A larger value means the object is more spread horizontally and mu02 is the variance along the y-axis. A smaller value here means the object is less spread vertically, and mu11 measures covariance between x and y. If it is non-zero, the object is tilted or diagonally spread. If it is zero, the object is aligned with the axis. So these central moments helps us to understand the shape and orientation of an object in an image. You just notice for the raw moment we calculate the zeroth order, first order as well as the second order. But in central moment we are directly calculate the second order. The reason is if you are try to calculate the zeroth order, that means if you are applying P and Q as 0, these two values becomes 1. So you totally calculate the addition of all intensity value. That is same as the raw moment zeroth order. That means it gives the area of the object. In the same way, if you are trying to calculate the first order moments, your value becomes 0. So no need for applying the first order values to the central moments. That's why we are directly calculate the second order values for central moments. The last concept is called shape models. A shape model is a mathematical or structural way of representing the shape of an object. Instead of storing every pixel of the object, we store only the important geometric information. This makes it easier to store, analyze, and compare the shapes efficiently in computer vision. These are all the common shape models we already discussed about it. That means chain codes, Fourier descriptors are used for storing the boundary informations, and moments, area, centroid for region based informations. And if the object shape is changed in dynamically, so active contours can be used. So by these methods we can model the shape. Once we model a shape, the next step is shape recognition, which means identify what the shape actually is. The process works in three main steps. First one is feature extraction. We first extract important details from the shape, like its boundary length, chain codes, Fourier descriptors, or moments. Second one is matching. Then we compare these extracted feature with stored model in a database. Then last one is classification. Finally, we decide which known shape the object is most similar to. In short, shape recognition allows us to go beyond just storing shapes. It enables us to identify and classify them. These are the simple diagram to understand shape model and shape recognition. I explained this one more step using this numerical example. From this object, we already extract the information like area, perimeter, centroid or chain code, etc. From this information, we should reconstruct the original image. That is called shape recognition. Using this parameter, we can identify this shape is a square shape having these values. For this shape models and shape recognition process, some issues are there. One of the major issue is occlusion. In shape model, we assume that entire boundary or region of the object is available. But when occlusion happens, part of the shape is missing, which makes the model incomplete or distorted. In shape recognition, the system must still identify the object even when only the visible part. So it totally misunderstood and reconstruct the wrong object. So we should handle the occlusion both in shape modeling and shape recognition. Suppose this is the given image means these are all the shape model parameters. But in case of occlusion image, this object is interpreted as rectangle instead of square image. Handling occlusion by means of different parameters like global descriptors, shape completion or model fitting, partial matching and multiple features. Suppose this is the occlusion image. From these various parameters, we identify the missing values are triple one that can be added in appropriate places and identify the total size of the object and add the necessary zeros to reconstruct the original image. So using these different parameters, you can handle the occlusion. From this unit, we understood different methods of shape and region analysis in computer vision. including binary, boundary-based, deformable, and region-based approaches. We also learned about advanced shape models and how to handle occlusion. Notes are available in the description part. You can download it. If you are having any queries, you can comment it. And thank you for learning with me. See you in next session.